Okay, let's fill out our learning card for experiments. We're going to start over here where it says reflect. And this is an acronym for some of the things that we need to remember when we think about experiments. The first thing that we want to look at and recognize when we're looking at an experiment is what is the response variable? And what is the response variable? Well, I'm going to use this little table over here, this little graph over here to as our example. So the first thing that we're going to look at, number one, says what will be measured in the end? Well, that's the response variable. What will be measured in the end? For this particular experiment, what we are measuring in the end is distance. And that distance is going to go on the vertical axis right here. The second item that we're going to look at in this reflect is E, the explanatory variable. So we have the response variable and the explanatory variable. Well, the explanatory variable is number 2 here. What variables do you think will cause the response or explain the response? So the explanatory variable is used to explain how we are getting the response variable or how it affects and causes the response variable. So in this particular case, our explanatory variable is going to be a particular drug. So you can see here that on the horizontal axis for this graphical display, the drug is broken into different doses. And we're going to talk about that here in just a second. We're actually going to cover F and L at the same time. And F and L stand for factors and levels. So for this particular experiment, what we're going to have is actually two factors. The two factors that we're going to have are going to be the drug that is given and administered, and also the hydration. So the context that we have here is a person is running long distance, and they are going to drink water or not drink water, and they're also going to take a particular drug, and a particular drug with a particular dose. So we're going to look at the factors first. The two factors, again, that we have are drug and hydration. So I've put these up here underneath factors, drug and hydration. Now, once we figure out what the factors are going to be, each one of these factors has levels. You can see number 4 here says levels of the factors. So let's start off with our drug factor. There's actually going to be 3 levels for our drug factor. The 3 levels will be no drug at all, a half a dose, and a full dose. So once again, the factor of the drug level has 3 levels: no drug, half a dose, full dose. Now, what about the hydration? Well, for the hydration, we're just going to have 2 levels. Yes, they are going to drink water, or no, they are not going to drink water. So here you can see that the factor of hydration has 2 levels, water or no water. Now I want to point out that the factors times the levels, if we multiply the number of factors times the number of levels, that leads us to something called the number of treatments. So I'm going to fill in E, C, and T all together. This actually forms one big sentence. So when we put all this together, what we can say is this: the factors times the levels, or the number of factors times the number of levels, is equal, or that equals, all possible combinations, which are also known as treatments. If we look over here, what we have is a factor of drug and hydration, and then I look at these levels. Now really what I'm doing is I'm taking these 3 levels and I'm multiplying times these 2 levels. So there's 3 levels here and 2 levels here, so 3 times these 2 is going to give me 6 treatments altogether. So really what I have for the treatments is all combinations of factors and levels. Here's a nice little visual representation for the treatments. H2O, or the water, yes and no, with each one of the drug doses. So yes water, no drug. Yes water, half of a dose. Yes water, full dose. And then so on and so forth with no water, no dose of drugs, no water, half a dose, and no water, full dose. So now we look at question number 6 here that says, who or what will you apply these treatments to? Well, who you are applying the treatments to or what you apply the treatments to are called the experimental units. Another note that you want to may add on here along with experimental units is that if you are experimenting on people, so who you will apply these treatments to, if you're experimenting on people, you could call those experimental units test subjects. So people are called test subjects, but if you're experimenting on animals or plants or things like that, you would call them experimental units. You could call people experimental units as well, but sometimes they're referred to as test subjects. I want to move over to this section of the learning card now, where it says improvements in design. Now, I really don't like that name, improvements in design. In fact, I probably would scratch that out and say alternatives in design, because sometimes blocking or using a matched pairs experiment or a double-blind experiment is not necessary and doesn't necessarily improve in the experimental design. So maybe instead of improvements, we should say alternatives in design. Let's start off by talking a little bit about blocking. Blocking is when you group your test subjects or your experimental units by a characteristic that may impact the outcome. So one example of grouping or blocking is to group your test subjects by gender, or maybe you would group your test subjects by race, or maybe you group your test subjects by whether or not they have allergies or by age. But if you are grouping by some kind of characteristic before you administer the treatment, then that is called blocking. And what that does is it helps to ensure that that each one of the treatments is given to each one of the groups. So that is a quick explanation of blocking. Matched pairs experiment is when you take your test subjects or your experimental units and you match them together in some way. So matching similar units to reduce confounding variables. So possibly a before and after. So if you run a race and then you take a particular drug and you run that race again, that would be your time before compared to your time after. That could be matched pairs. If you pair twins together or siblings or spouses together so that you are comparing the difference between the two spouses or comparing the difference between the two twins, that is a matched pairs experiment. Probably the most common is a before and after experiment. Now let's take a look at a double-blind experiment. That is when neither the researcher nor the test subject knows the placebo from the actual treatment. So over here you've got two guys that are blindfolded. So if the researcher is giving the treatment and the test subject is like, okay, thanks, but neither one knows if the test subject is getting a placebo or an actual treatment, then this is called a double-blind experiment. Part of the learning card that we'll look at is over here. It says statistical significance. So how do we know if something is statistically significant? Well, that's when we look at, were the results more significant than random chance? Now, we're really going to get into statistical significance later on in the course. But when something is statistically significant, that means that it is very different, or the probability that it happens just due to random chance is really, really, really small. So we'll get into that when we get into hypothesis testing. But for now, statistical significance, were the results more significant than just random chance? That's how you can fill that part in. I'm not going to worry about this last part where it says realism. Will the results transfer to real situations? But I don't need to go into details there. So there's your learning card for experiments. I hope you have fun in your stats class.